Can you see it? Can you see the slide?
Yeah,
Yeah,
Okay. And I'm also audible, right?
yeah,
yeah.
So let me start the session. First of all, happy Independence Day to all of you. And let me introduce myself. I am Moina Kushal, and I am the TA for this course, which is application of spectroscopic method in the molecular structure determination. And this is regarding assignment of week 3, where I am going to discuss some problems regarding the module, and that will be helpful for you. Some information about you, and you should. So that will be helpful for you to solve problems regarding this module. So, namely, in the last week I have discussed about techniques that we generally use, where we have discussed about this 13 carbon enamel and proton enamel also. And this week, the course model is mainly based upon uh, course model is mainly based upon the variable temperature enamel and also the determination of stereochemistry with the use of enamel spectroscopy. Yeah. So first, starting the module, uh, there were question that Professor Sankar Raman has explained that uh, the determination of the stereochemistry using enema technique, and there we have explained that the ketene structure, which is also which looks like this CH2, looks like CH2. Double one C, double one. So this kind of ketene structure, he has explained that when this is dimerizes, either it can form diketone or it can form lactone. What is the difference between diketone and lactone? In diketone, you will see, sorry, you will see two keto group, and in lactone is nothing but a cyclic ester. Okay, so among these, which one actually it prefers? It was explained using NMR that if you count the number of signals that is coming from this dimer, then you will understand that it actually evolves through the electron. Now there was a discussion about the difference of the chemical shift between this axial and equatorial hydrogen of cyclohexane. In cyclohexane, just discussed that this beta gamma bond anisotropy actually helps to distinguish these two hydrogens, because this equatorial one will have higher delta value due to this anisotropy than the axial one. Okay, so this actually will help to determine you that from the chemical shift of the hydrogen, you will be able to determine that in which position, the axial or equatorial position, the hydrogen is attached actually. Also, there is a determination of this anomeric hydrogen of a sugar molecule as alpha or beta. You can do it based on the coupling constant. So in anomeric carbon, like this. Okay. So in this anomeric carbon, wherever this hydrogen is alpha or beta, you can determine it either using this chemical shift value, what I have discussed for this cyclohexane molecule. So you can do the same thing, or you can do that on the basis of coupling constant. That I will show. Before that, different chemical values for extra and endo hydrogen for bicyclic compound, you can also determine it. I'm doing it here below. Suppose this is a bicycle compound. Okay, so the quality of my drawing. So this one compound, so this hydrogen and this hydrogen. Okay, so one is exo, another is endo. Now, can anyone tell me what is the name of this compound? IUPAC name? Anyone? What is the IUPAC name of this compound? Okay. Think
221 heptene.
again.
221 heptene.
221 heptene.
Cyclo.
Again.
Cyclo 221 heptene.
Yeah, bicyclo.
221 heptene.
Yes. 221
heptene.
2 in or heptene? Yeah.
2 in. Barabar. Yes.
Yes. This is the name of this compound. So if you know this, how to know this. So if you just count the number of carbon, you start from here, the bridget position, and go from this side. This is the double bond side. 4, 5, 6, and this one is 7. Okay. So this there, this side is 2 carbon. So 2, 2, 1, and since 7 carbons are there, so hept, and in 2 position there is double bond. So this will be heptowin. This is how the bicyclic compounds are named generally. So there should, since there is a double bond, so due to this anisotropy, so this hydrogen and this hydrogen will show different chemical stage value. If I remember, if this is OH, if this is OH, then these actually will show nearly 3.5 ppm, nearly. And if this is OH, take another color. If this is OH and this is hydrogen, so this hydrogen that will come nearby 3.9, 3.9 like that. Okay. So by using this NMR, by looking at this chemical shift value, you can just differentiate between which was in endo. Okay. So what I was telling about that anomeric position, if you want to know that whether a sugar molecule is alpha or beta, so you can tell it on the basis of coupling, on the basis of chemical shift. Also, you can do that same thing using this theory, which is known as Karplus-Kornion theory. So what this Karp-Conroy theory says, this is the relation between this J value with the dihedral angle. Okay, so these follow actually this rule, and whenever if you know that this coupling, this value from this if okay, yeah, so here you know the dihedral angle will differ for alpha or beta anomeric carbon. So with a particular value of this dihedral angle, you will get a particular value of J. Okay. Now whatever J you obtain or whatever coupling constant you obtain from your NMR, you just match it with it. Then you will understand that this much of coupling constant actually tells you that this orientation is alpha anomer or it is beta anomer. Okay. So by using this equation or this theory, you can easily predict that whether alpha anomer or beta anomer is present in the compound or not. Now you can also do one thing, you can just separate cis and trans stilbene using NMR. Okay. So for stilbene, so for these two cases, you will see there will be a difference in the coupling constant. So from the value of this coupling constant, you can easily determine that which one is cis and which conformation is trans conformation. And also there is a determination of relative population of different conformer using the coupling constant value. Okay. So if you know this coupling constant, and if you, since you can correlate your coupling constant with your dihedral angle, so for different conformation, if you know this dihedral angle, you know how much of this J value will come. You just match with your spectra, take the quantitative value that this much of J is coming, and from that you can easily tell that how much of relative population is there with respect to one other conformer. So these are the experiments you can do, and these will help you to determine the stereochemistry. And next, you can do that same thing using NOE. And in case of NOE, which is nuclear over Hauser effect, you can use the difference spectrum. What is difference spectrum? Difference spectrum is nothing but you are recording your NMR in the presence of NOE and in the absence of NOE. You are just taking the difference between them. Then you will see the effect of NOE, how NOE is affecting the chemical shift. Okay. So with the use of NOE, E versus Z stereochemistry determination, you can do it in the absence of scalar vicinal coupling. Suppose you don't have this vicinal coupling constant. So how will you do that? That whether a compound which you have got is cis or trans. Okay. So I have the example with me, the compound. There is CH2 whole 6 CH3. That was discussed also in the lecture. But this one, okay. So here you can see that if you want to know this conformer, you just give some just give some of resonance, or you can say you decouple, or in the good language you can say you can want to saturate this proton signal, and you know that NOE or nuclear over-Hauser effect is actually affect nearby protons. Okay. So if you want to saturate this, so the nearby proton, this will be affected much more. Okay, but if it will be in the opposite side, the effect will be very small, it because it will be very far away. Okay, so you just saturate one proton and you see that how does this affect its nearby partners. So there, from there you can confirm that which types of geometrical orientation the molecule has got. And also from there, you can determine the ratio of enantiomer. You have seen this in the lecture of this Mosar's acid chloride, where you have, suppose you have R alcohol, okay, and suppose you have in the mixture you have S alcohol. So here you can just add this any kind of R or S acid chloride. So what will happen? They will form ester. What kind of ester? This ester will have two types of stereochemistry. Either it will be RR, because R of this acid with R of this alcohol, or it will form RS. Okay. So doing with pure R and pure R acid chloride and R alcohol, you know the NMR positions or the peak positions of where this is coming. And in the racemic mixture, you can easily differentiate that where S is coming, because and you also do that using S alcohol. So from there, if you know the intensity, from there you can easily calculate that what is the ratio for this R and S alcohol. Okay. Then stereochemistry can also be determined using a lanthanide shift reagent. Okay. And this was you have discussed in the previous module that you just have a E or Z isomer. Okay. So I think I have example. Yeah. Here, suppose this is the example that was discussed. So in these two cases, you will see that if you suppose that any europium, which is a lanthanide, UAL6, I suppose, it will coordinate with OH. So this methyl group here, and if it is coordinating to here, this UL6, so these two chemical shift of these two methyl will be very different. Okay. In the first case, if you see, as you increase the concentration of this lanthanide shift reagent, you will see according to this equation that I have discussed in the previous class, that 3 cos square theta minus 5 minus 1 equation, that will show kind of delta nu by nu versus I think 5 was there. So if you sorry, this will be concentration of this lanthanide. Yeah, you are increasing the concentration. So there will be something which will be very much affected, and there will be something very less affected. Okay. In this case, you see this methyl, since it is cis to this OH group, so it will be very much affected. Here it is very far away from this OH, so the lanthanide shift reagent, as you increase the concentration, that will not affect your methyl. Okay. So you will see that for E isomer, you see this will be very much changing, but for Z isomer that will not much change, because that will very less effect using when you use this lanthanide shift reagent. And from that you can easily determine enantiomeric axis using lanthanide shift reagent, and also I have mentioned this Mosar's acid chloride. From there you can easily calculate that what concentration is the R isomer, what is the S isomer, and from there you can easily calculate this enantiomeric axis. So in the next module, there was a discussion on effect of variable temperature NMR. Okay. So why you use variable temperature NMR, or what kind of information you can get from this variable temperature NMR? First information and foremost information you got is conformational change. Suppose your molecule, you have some compound. Okay, so it is undergoing a conformational change. It is undergoing some conformational change. How will you detect that? In the room temperature, if in the room you want to know, or if you want to monitor the conformational change in the room temperature, you will see that it is very fast. So you cannot detect any of the species. So whatever you do, you will go to the low temperature where the activation energy is not provided for these conformational changes. the last class, in the last question, I have solved some problem regarding like this, that when you go to the low temperature, you will see that two forms coexist. Okay, so using this variable temperature NMR, you can easily confirm these conformational changes if in a if it is happening in a molecule. Also, from this restricted rotation of CH and CC bond. So if you go to low temperature, a certain properties of the molecule actually changes. Okay, so if you want to see that what is the effect of the CC and CC, what happens when the restriction of CC and CX bond. CC and CX bond actually they are very single bond. They are single bonds, so they can easily rotate. So you can stop this rotation or this movement of the CC or CX bond using low temperature NMR. Or if you go to the low temperature, you can just stop this rotation. Also, you can monitor the aggregation phenomena. Okay, so in the aggregated state and in the monomeric state, or in the aggregated state, you will see there will be a concentration dependent NMR shift. Okay, so there will, from this concentration dependent NMR shift, you can calculate a lot of things, which I will come later. And also you can monitor these fluxional behavior properties of the molecule. So using this variable temperature NMR, you can also monitor the fluxional property of some molecule. So these are the usefulness of variable temperature NMR technique. And also there is a concept of coalescence temperature. What is coalescence temperature? Coalescence temperature actually tells you that suppose you are just lowering your temperature, you are seeing only one peak, and at some temperature from this one peak you have got two peak, or the peak is actually getting separated. So that temperature is also known as coalescence temperature. And from this coalescence temperature, you can easily determine the rate constant for this conversion using this relation, which was mentioned, delta Kc equals to pi delta nu by root 2. Okay, so by this relation, you can easily determine from this coalescence temperature that how, in which rate this is actually changing. Okay, so here I want to mention one thing. Yeah, so here what type of molecule is mentioned, which is called fluxional molecule. What is fluxional molecule? Can anybody tell me?
Sir, molecule which changes its structure. Like
Molecule.
ammonia is phloxynial. Ammonia goes from one pyramidal to planar to the other pyramidal. That is, inversion takes place.
So that is a fluxional molecule.
Yes, sir.
So what we were saying, that any molecule that actually changes its conformation, that is a fluxional molecule, right?
I think so, sir.
Okay. Anybody else? What is a fluxional molecule? If you have seen the lecture, you have seen this mulvalin, which is a fluxional molecule, and from there you can just easily tell that what is a fluxional molecule. Anybody else? Okay, fine. So it is actually happened that you see in some molecules or some organic molecules, the bonds actually rotates or that moves, and if you go to the very low temperature, you will be able to monitor what is happening in the molecule. Okay, but all this is a special case of this fluxional molecule. Who is mentioned is correct. This is a special case of this fluxional molecule. But actually, fluxional molecules actually tells that upon this change or upon interchange of these atomic positions, okay, upon change of or upon interchange, upon interchange of these atomic positions, okay, upon change of or upon interchange, upon interchange of these atomic positions, okay, upon change of or upon interchange, upon interchange of these atomic positions, okay, upon change of or upon interchange, upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, upon change of or upon interchange of these atomic positions, okay, up of equivalent, it could be chemically, it could be magnetically, not protons, it's atoms, there will be some spectroscopic signature. Then we will say that it is undergoing a fluxional change. What kind of spectroscopic signature? You will see in the spectra that the spectral modeling is happening due to Heisenberg's uncertainty principle. Okay, but it could happen that beyond this Heisenberg's uncertainty principle, if your molecule or if in your molecule, if the atoms are interchanging their positions, you cannot monitor it in the room temperature. But if you go to the low temperature, you will be able to get different conformations, and you will see the change in your line shape of the spectrum. Okay, so this change in the spectral line shape actually tells you that in your molecule, the positions of the atoms is actually gradually changing. So this way you can define this molecule as a fluxional molecule, which is a good example of this Bulvelin. Okay, if you have read about organometallic chemistry, you will find this pyroxene kind of thing, eta 1 CP, eta 5 CP, I think CO whole 2 or something else. I exactly didn't remember the ligand like this. Okay, so here the rotation, you cannot monitor it in the room temperature. You have to go to the very low temperature where you will be able to differentiate between these two rings, these two CP rings. Okay, you cannot differentiate in the room temperature. So this interconversion is actually happening in such a fast scale, or the position change of the atoms is happening in such a fast scale that you cannot monitor. And you will see, and if you go to low temperature, due to this interchange of the position of the atoms, you will see a change in the spectral positions, or in the spectra you will see some change. Okay, so these kind of molecules are known as fluxional molecules. So coming to the next point, what I was asking, actually talking about Bulvelin, most fluxional molecule, it shows degenerate rearrangement. Okay, so Professor Sankaranaman has explained about this. This is a degenerate rearrangement. So degenerate rearrangement actually tells you that from upon rearrangement, one molecule is going to its own form upon rearrangement. Okay, so rearrangement actually gives back same molecule, gives back same molecule upon rearrangement. What kind of rearrangement it undergoes? It undergoes co-rearrangement. Okay, which is 3 prime sigmatropic shift. If you have seen this his lecture, you will see that the change in the positions, or in the change, the making and breaking of the bond, you will see there will be a shift of this 3 prime position. Okay. Next, you can also monitor double bond isomerization of aniline kind of system using variable temperature NMR. Okay. So normal in room temperature, you cannot differentiate between two protons in aniline kind of system. Okay, so if you go to the low temperature, that will show the different environment. So what is double bond isomerization? Double bond isomerization is nothing but the change of the position of the double bond. Okay, in the benzene, benzene show resonance. What happens after resonance? The position of the double bond actually changes. That's the same thing of double bond isomerization. That is, the position of the double bonds actually changes, and from there, the environment that is faced by different protons, which will be different in the low temperature, and you can easily monitor it using the variable temperature NMR. Also, the study of carbonium ion or carbocation using rearrangement in non-bonded system, which is another bicyclo kind of system, you can monitor, and you can see that 3 types of or 2 types of different carbons, and from there you can easily determine that if it is changing is going through any intermediate or not. You can easily monitor from this carbonium ion rearrangement. Also, in FeCO4 fragment movement you can monitor it for this tetramethylalline kind of system. Alline is known, alline is actually known, very known for one kind of thing, because it actually have chiral plane. So this is nothing but tetramethylalline. Okay. Now, if you have some FeCO4 kind of thing, FeCO whole 4. Okay. So this group actually attaches to this double bond. Okay. So what you will see? You will see that at very low temperature, or minus 330 degree, you will see that this, you cannot differentiate between these two protons or these two methyl. Okay. But these are different. So at particular temperature, minus 30 degree, okay, so you have seen this two is in the plane and another two is in like that. Okay. So you can differentiate between these two, but you cannot differentiate between this one and this one. Okay. So you will see three signals corresponding to this ratio of 1:2:1. But as you increase the temperature, what will happen? The bond, you will see there is a movement, and you will be again get only one signal. Okay, so all the methyl becomes equivalent at very high temperature. Also, the dimerization of AlMe3, aluminium, trimethyl aluminium actually shows this banana bond kind of structure. If you know about banana bond, it's good. If you don't know, tell me. So if you see the structure of B2H6 kind of thing, it will show like this, the 3 center 2 electron bond like that. So this is the terminal methyl and this is the bridging methyl. So you will see there will be a difference. If you go to low temperature, you will see the dimerized form of this AlMe3, and there you will see the two different peaks will be observed for two different kinds of methyl group which is present in the molecule. As you increase the temperature, this dimerized kind of thing will break down. You will only get one peak due to methyl. Okay. Now, at low temperature, you can also do one thing, that exchangeable hydrogen of methanol. You can just see that the methanol, what I have told you in the earlier problem solving sessions, that this OH is exchangeable with the solvent. If you have D2O or DCl kind of thing, this H actually exchanges with this D2 or DCl. So if you have this kind of solvent and if you have this molecule, so at room temperature, this race is so fast, the exchange is so fast, you cannot monitor it. What you will do? You will go to the low temperature. What will happen? Low temperature, the exchange rate will be decreased. Okay. So the splitting of this methyl hydrogen, that will be affected by this neighboring hydrogen. Okay, that was initially absent due to through fast exchange of this hydrogen with the solvent, but here you will see that this CH3, that will be affected by this hydrogen, and similarly you will get peak for this one, this hydrogen. So the coupling between this hydrogen and this CH3, that will be taking place at the low temperature, which is impossible at the room temperature. So this gives you, or this tells you actually the utility of this low temperature measurement or temperature dependent NMR. So about the association or dissociation, I have told you that it is completely.
Excuse me.
Yeah.
This is regarding the exchangeable H of methanol.
Yeah.
In case if instead of O, if nitrogen is there, the same thing will happen.
Yes.
It's applicable for all type of heteroatoms.
Yes, it will applicable, right? But it actually depends upon the temperature or the and also the exchange rate. Okay. So the exchange rate between this OH and NH2 with the solvent will be different.
Yeah, as far as the understanding of NMR, we know in the normal case of recording of NMR, we never have a coupling between the CH3 and the OH protons.
Yes, exactly.
But if you do it at a lower temperature, we can expect this peak here.
Exactly. You will see the splitting due to this hydrogen.
The
This will
splitting will be like the n+1 rule, same way.
Yes, exactly.
And we may not get. I mean, this is applicable for all other type of retroatoms.
Yes, that depends if the hydrogen attached to that heteroatom exchanges with the solvent. In that case, it is applicable. Yes.
But one more doubt is how to know what is the temperature you have to keep it to have this kind of a splitting. We are saying low temperature, high temperature. How do we know what temperature we need to do that?
It means your question is how low is low, right?
Yeah. What sometimes low means it may be even below 0.
Yes.
So how to determine what temperature we have to do that to have such kind of understanding of a splitting pattern or getting a signal?
Okay, so you can actually this actually any process like this process what I was telling you about this exchange, this actually associated with some activation energy. Okay, so if you just give this activation energy, if you cannot know that how at what temperature it will be just not exchange or the rate of exchange will be decreased. So you have to just load the temperature and you have to monitor at every some temperature that at what temperature you will get peaks corresponding to this hydrogen. Okay, so this is just a trial and error kind of thing. So beforehand you cannot know. Yeah, either using theory if it's predictable, but in experiment if you want to know, you have to do the low temperature. You have to go to low temperature and at any temperature where you will see the difference of the peak or the peak splitting due to this weight, and then you can determine that at this temperature actually this exchange of this hydrogen is actually prohibited. Got my answer?
Yeah, fine.
So this association and dissociation in you can actually monitor using this NMR technique. Okay, how can you monitor? You will see the shift in the positions of this peak is actually dependent upon the concentration. Okay, if you decrease the concentration, you see that the positions are shifted. Okay, from there you can actually detect the many thermodynamic parameters, like you can determine this if suppose to A is going to A2, from there you can determine this equilibrium constant, which is nothing but the concentration of this dimer divided by concentration of monomer whole square. Okay, so this from this physical chemistry knowledge, and here if you do that, then and from the integration the concentration, then you will be able to go to Kc, and from there you can easily determine this delta H, delta G, etc., delta S also from this thermodynamic parameter. So you will need to monitor it at different concentration. You need to monitor it at different temperature. Okay, because temperature actually affects the association or dissociation rate. Okay, so these are the things that Professor Sankar Raman has explained about NMR. So I'm now going to solve some problems regarding this, which will be helpful for you. Just a minute. Yeah.
Sir, I have a question.
Yes, sure.
Is there any formula to calculate the molar ratio of two different enantiomers present in a mixture from the integration ratio data?
Mm-hmm. If you
What is that?
again your question.
What is that formula?
What is that formula? Oh, yeah. So I have shown you that from this integration, you can easily determine what is the molar ratio. Okay, from the integration, how much hydrogen is present or how much proton is giving that signal. Okay, so if you see that in the first lecture, I have shown you that from paranitro aniline or paranitotoluene, I cannot remember what compound was that. From there, for ortho and para, I have shown that integration of 56 and 28, I think. From there, I can just tell that the ratio was 2:1. You can tell it that what is the ratio of this molar ratio. Okay, so you'll be able to just tell this molar ratio. Yeah.
Is that video available?
Yes.
Where you told that?
Yes. In the first lecture, first series, week
Okay,
1 assignment. Okay, you can see it in the YouTube. So there was a question of for paranitro orthonitro aniline, or I guess compound exactly I cannot remember. Orthonitro.
Okay, sir. Thank you, sir.
Okay. So there the integration are given that of 56 or something, and from there you have to get the molar ratio of these two compounds, and where there they have to just take the ratio of the integration where you will get the molar ratio. Okay.
Yes, sir. Yes, sir.
Okay, fine. Okay, now coming to the question, the first question is the aromatic region, only aromatic region of the proton NMR of spectrum of N-methyl 2,4,6 trinitroaniline is shown below at two different temperatures. Explain the spectral pattern at this temperature based on the dynamic process that is involved. So the question is actually telling so you see the question is actually telling that at minus 60 degrees Celsius you are seeing this kind of AB quartet kind of pattern. Okay, but at 36 degree plus 36 degree you are seeing a single peak for the compound N-methyl 2,4,6 trinitroaniline. I am just drawing the structure here. Yeah. Okay. So aniline is NH2. There is mentioned as N-methyl aniline. So there will be one methyl, another will be a hydrogen. And also in the 2, 4, and 6th position, there is NO2 group, right? So only hydrogens are left here and here. These two meta position only vacant for hydrogens. Fine. So from this structure, these hydrogens, these aromatic hydrogens, the observation is like that at low temperature you are getting a AB quartet kind of thing, and at high temperature you are getting a singlet. So can you tell me how will you explain that? Try it. You are seeing a AB quartet at low temperature. This is an example of variable temperature NMR. You are seeing, yeah.
In a positive mode, I mean a higher temperature or at a room temperature, the transition of this proton between these two will be faster, and so we'll be getting a singlet.
These two.
Yeah, that is the reason that we are getting 36.2, we get a singlet, because of the reason that we are not able to detect the transitions of the protons between these. It's very fast.
Yes.
Whereas at low temperature, we can able to differentiate these two protons, which are going in a very slow manner. Transition of the protons.
Why? Why it is going in slow manner? Yeah, you are correct. Your answer is correct. But there is some reason that it is going in the slow manner. But there will you need to put some barrier that it cannot go fast. Okay. So what is the barrier?
So there will be resonance from the lone pair of nitrogen to the benzene ring.
Exactly. Correct. So this nitrogen lone pair will be okay. Let me do one thing. So I write NO2 like this. Now yeah. So this lone pair of nitrogen will go here. It will go here. So there is an extended resonance. Okay. This is Me. This is H. There will be a plus charge. There is another NO2. Yeah. So this is the structure that if nitrogen lone pair get involved in the conjugation, then there will be this kind of structure. Okay. Now, if this rotation, if you need to stop this rotation, this CN bond rotation, you need to stop. When your nitrogen lone pair is involved, you see the CN bond got a double bond character. Double bond cannot rotate. Single bond can easily rotate. The probability of rotating the double bond is very, very, very low. Okay. So at that condition, what we'll see, these two hydrogens will be different. Okay. In that environment, when these two hydrogens are different, you will see a heavy quartet kind of pattern, which is observed here at low temperature. That you see a heavy quartet kind of pattern here. But at high temperature, since this process is very, very fast, you will see that only one kind of hydrogen is present, and these two hydrogens are becomes equivalent, and they will see only one kind of peak. So this is the answer, that at a high temperature, fast rotation of CN bond leading to singlet peak for equivalent hydrogens. But at low temperature, the CN bond's rotation stops. Okay. So, and the lone pair of nitrogen that actually comes in conjugation with the aromatic ring. Hence, the two protons that becomes different, and so AB quartet kind of structure due to beta coupling. Right. So this is the reason you will see this kind of structure, and this is the reason that you need. This is the reason you need a low temperature NMR or a variable temperature NMR, from which you will be able to determine that this kind of stereochemistry or this kind of orientation. Okay. So,
Sir, is there will be chemical shift difference between these two protons at low temperature?
these two.
These two protons will have a different chemical shift value.
Yeah. This will be somewhat difficult. Yes, different. But at the room temperature, whatever you get is just the averaged out value of these two. Okay. Is that okay?
Yes, sir. Yes, sir.
But how to know which hydrogen is going to the downfield shift, sir, or which one is on the upfield shift? Because in this structure, it looks like the environment of nitro is almost the same along with these protons here.
Yes, it's almost same. Okay. So
So
the difference will be very low. This is actually a zoomed version. Okay.
okay.
So the difference is very low. These
Okay.
two are almost identical, and that's why you will see this AB kind of quartet type kind of structure, and the separation will be very, very much less.
So no need to give the chemical
Yes.
shift values for this particular question.
Mm-hmm.
Whether we need to give the chemical shift values approximately what would be.
No. You don't need to give the chemical shift value. It's important here the concept.
Okay.
That's why it is changing.
Thank you. Thank you.
Okay, so going to the next question. Yeah, I think this question was not in the assignment. I have given it. So the 1H NMR spectrum of 3,3-dimethyl butyl magnesium chloride is given below. Okay, you have to explain the observation. The same thing, you don't need to give the chemical shift value. You just need to explain the pattern or what kind of phenomena is happening in this case. So I'm just drawing the structure. Okay, so 3,3-dimethyl butyl magnesium chloride. This looks like something like this. Yeah. See, this 3, suppose 1, 2, 3, 4. Okay. So here you see this name is 3,3-dimethyl. 4 carbons are there. So 3,3-dimethyl butyl magnesium chloride. So this kind of reagent has a particular name. You know it. Which is, what is the name? This kind of compound.
Is it Grignard reagent?
Exactly. Exactly. Grignard reagent. Yes. So the question is, the proton NMR spectrum is given at different temperature. You see here, this is plus 32 degrees Celsius and it is minus 53 degree. Okay. Here you see a 3 photon pattern, 3 singlet kind of pattern, but here you see a very much difference in the spectral positions or the spectral profile. So who can explain this reason? What is happening here?
Sir, at a higher temperature, the bond between carbon 2 and carbon 3 is rotable. That is, it is rotating. So the 3 methyl groups are in equivalent environment. So carbon 3 gives, these methyl groups give one signal, and the other 1 and 2 carbon protons, so 2 different signals. So 3 signals will be there in high temperature.
At low
Due
temperature?
to CC bond rotation. Due to CC bond rotation, sir. 2-3 bond rotation.
2-3 bond. Okay. And at high temperature, what happens?
Sir, this is at high temperature. At low temperature, there will be.
Low temperature, what happens?
At low temperature, let me see, sir.
Yeah, you take time. You were telling this bond rotation, right? You see. Okay. Anybody else? Single bond. Okay, I can make life a bit easy. Okay. At low temperature and at high temperature. So you will get 3 peaks. But at low temperature, you get almost 8. Okay, if you there is some small peaks, you count, it will be 8 peaks almost. Can you explain? Okay, let me explain it. Okay, let me give you another clue. This is not the whole spectrum. This I should have mentioned. This is due to this hydrogen. Now you can explain this hydrogen. You see, this will give you 2 hydrogen, 2 plus 1, 3, triplet. You will see triplet. But at low temperature, what happens? No, I have given you enough hint. Now you will be able to tell me. See, this hydrogen, this one, this has 2 equivalent hydrogens here. So this will give me 2 plus 1, 3 signal. This is a triplet. Triplet kind of thing you will see. Okay. But at low temperature, what will actually happen? Why it is not giving the triplet?
No idea, sir.
Before giving the answer, I just wanted to confirm, how do you account for 8 peaks here? Can you explain it in the peaks if it is given at the low temperature of minus 53?
Okay, so since I know the answer.
No, you don't reveal. Please don't reveal now the answer. Let me check whether you are getting 8 here.
Yeah.
Then
So
because What is the numbers here? If I count it, it comes like 7 only, but I don't
Yeah.
know.
But according to since I know the answer, so if I count it, how many it will come? It will comes at 8. So there is a small peak like this. Okay. So that will be very low. I mean, this is completely out of this resolution. Okay. So that will give you 8 peaks. I am just telling it.
Okay, okay. Please go ahead with the answer.
Okay. Anybody else? 2-bond coupling. Okay, let me go to the answer. So this is the answer. The compound actually exists in the most stable transform at low temperature. Transform at the low temperature, and so this kind of splitting pattern. Okay, so if I draw a Newman projection, take a new slide, that will be helpful for you. So what I was telling, this compound okay, so this is the compound. Now if I draw the Newman projection of this, so here I'm not changing this tertiary butyl group, which is fixed. This CH2 I am writing like this, and this CH2 writing like this, and here is your MgBr. Since this is the anti-conformation, so at very low temperature, this is the most stable conformation. Okay. Now, see this hydrogen, suppose I name it as A, okay, and this suppose I name it as A prime. This hydrogen I name it as X, and I need name it as X prime. You see, this and this hydrogen will be different at low temperature. Because why it will be different? Because the environment you see here is among these two hydrogen, they will be very close but not equal, not same. Okay, and since they are diastereotopic, these two hydrogens, they will show every kind of quartet. Okay, so these hydrogen at very low temperature will couple to this hydrogen to give you doublet. Okay, with this hydrogen again doublet, so doublet of doublet. With this hydrogen it will again couple, this will give you doublet of doublet of doublet. So if you know doublet, you get 2 lines. In a doublet of doublet, you will get 4 lines. In doublet of doublet of doublet, you will get 8 lines. That lines you just see there. Now, what happens at high temperature? Now I will explain that it is actually, if you see, if you know the structure of this Grignard reagent, it actually have a carbanion kind of structure here. Okay. Carbanion kind of structure. Now, this structure actually can interchange or rotate at high temperature. Okay, so this is the rotation. So here, what kind of structure you got? You got A prime, because two hydrogens are different here. X prime kind of structure. Okay, at low temperature. So rotation will give something like this transition state. I am just drawing this transition state. Okay, here will be the carbon ion. Okay, so your Hx will be here, Hx prime will be here, and since it is rotating, so some point of time Ha will come here, Ha prime come here. This is an in-between state. Okay, so it is just this. Okay, so it is just getting rotated like this. Okay, now again rotation, that means if it keeps on rotating, it is seen that you will end up like this. It's a very spontaneous process, it will happen automatically. So it's Hx prime, and you will have carbon layer like things here. Okay, this Ha prime here, and Ha will goes here. Okay, so this is just completely rotating the structure. This is the structure, you just change it, it will completely rotate. Okay, Ha will become in the position of Ha prime, and Ha prime will be in the position of Ha. So this happens actually at high temperature or room temperature, whatever you are seeing here. At that temperature, this is actually happening. So rapid conversion, you cannot then differentiate between Ha prime and A. Okay, you will see the same signal for these two. Similarly, you cannot differentiate between X and X prime. Okay, they both become the same. So it becomes A2 X2 kind of structure. So what is the change at a high temperature, high T? So what is the change at low temperature? You are seeing the protons environments are different completely. Okay, so you see A prime X prime kind of pattern, and you will see the quartet and how this is getting 8 peaks. I have explained. Now it is when it is actually going to the higher temperature, what is happening, that this carbonium kind of structure, because this magnesium to magnesium bromide, if you know this little bit of this Grignard reagent, this is a metal, so it will hold this electron density, and there will be a negative charge here. Okay, so there will be a delta plus kind of thing, and so this carbon will be carrying delta minus. So it will kind of carbonium kind of structure. And here you will see that the bond rotation is so fast that you cannot differentiate between A and A prime. Similarly, you cannot differentiate between X and X prime. So you will see this A and A prime are same, X and X prime are same. And since there is two hydrogens, okay, there is two hydrogen, and since they will there is two hydrogens, so you will show a triplet kind of thing here. Okay, so this is the explanation that I have written here. The compound is exist in the transform, but high temperature becomes A2X2 kind of system due to rapid rotation around this CC single bond. So the possible existence of carbon and rotation is expected in this case. So this is the logic behind this kind of spectral pattern that is observed for 3,3-dimethyl butyl magnesium chloride. Is this clear to all?
Yes,
Okay.
sir, cleared.
Okay. So moving to the next question. Yeah. Oh, I have shown the answer. Anyway, fine. So question is, the alkylation of diethyl malonate with ethyl bromide gives two products, namely monoalkylated and dialkylated. So you have to assign an appropriate structure for each of the case. Okay. So what is the structure of this malonic acid? Who can tell me?
CH2CO O COH.
CH2.
Twice. CH2 C double bond O
Hmm.
O
O.
CH2 CH3 twice.
How twice?
No, you're writing CH2 malonic acid.
Mm-hmm.
I'm just
malonic acid. Then I will go to diethyl malonate.
yeah, CH2 COO
CH2COO.
H twice.
So not ethyl. Okay, fine.
Yeah. If you include two ethyl group, then it will be diethyl malonate.
So this will be like this, right? The valence is not satisfied.
Sir, CH3,
CH3,
CH2,
H3, CH2,
O,
O.
single bond, carbonyl group,
Yes,
CH2,
H2.
again carbonyl group,
Yeah.
and OCH2CH3.
Oh, you have told me.
I have solved this question, sir.
Oh. Okay, good. So when you have solved this question, what is your name?
Yes, sir.
What's your name?
My name is Prakash Kumar Mandal.
Oh, Prakash. So Prakash, when you have solved this question, do you remember the structure of this malonic acid, or you have seen from Google?
I have seen from Google.
So actually, I was asking about this malonic acid. So malonic acid is nothing but what Prakash has said is correct. This will be COOH kind of thing. So this will be C double bond O, this OH. Okay, this is the malonic acid. These two hydrogens are there. So another way of remembering it, when I have remembered this, so there is a rule. I don't know what rules. Anybody have idea about this? OMSGAP, OMSGAP.
Yes, sir.
What this tell?
O means oxalic acid, COOH, COH. M means CH2 is incorporated in between COH, COH. Succinic acid.
So for dicarboxylic acid, generally this rule actually happens. COOH kind of CH2 whole N. Suppose this is a dicarboxylic acid. Okay. So if you cannot remember that what is oxalic acid, malonic acid, succinic acid, glutaric acid, whatever. So you just write this kind of structure. Okay. Now you just put value of N. Okay. You just first put N equals to 0. So there will be no CH2. So this structure will be COOH, COOH. What will be the name? This will be oxalic acid. Now you put N equals to 1. So there will be COOH, CH2, COOH. So you go O after O, it is the same. So M means malonic acid.
Excuse me.
Yeah.
If N is equal to 0 means it will be COOH, CH2, COOH, no?
No, it will be COOH, COOH.
That means the whole CH2 will be 0.
Yeah, N is 0, no CH2 is there. Okay, so N is the number of CH2 between these two carboxylic groups.
No, I was thinking CH2 is N number is 1 or 0, something like that.
No. N is actually defined that how much CH2 is in between the COOH. If there is 0, that means no CH2 is there. 1 means only one CH2.
Okay.
Okay. So if I go to N equals to 2, this is succinic acid. So if I go to 3, what is the name? G. This is glutaric acid. N equal to 4. This much of you need just. This is adipic acid. Okay. So if for any dicarboxylic acid, if you cannot remember that what kind of the structure it actually resembles, you just write this formula: COOH, CH2 whole N, COOH. Now you put N equal to 0, 1, 2, 3, 4, and you will follow OMSGAP, and you see that if M is in the there, so only one CH2 will be there. So your structure will be like this.
What about if n is equal to 5, sir?
N equals to 5, you will go to this P. This is some palmitic acid or something this like this. Okay. So generally, this kind of this up to this actually very much it is needed. P is like palmitic acid or kind of this one. Okay.
Sir, in the OMS GAP, T is written, why T is written, sir?
T.
Yes,
Oh no,
sir.
it is that arrow. Okay, sorry for this.
Okay, sir.
This is the arrow. Okay, this is not T. I am just mentioned this malonic acid here.
Okay, sir.
Okay. So what will be the malonic acid? COOH CH2, because only one CH2 will be there, and COOH. So Prakash, do you know need to Google it this time?
No, sir. Thank you.
Okay.
I will never forget this.
Yeah. Good. Mhm. Yeah. Now coming to the main question. Okay, I should take a new slide. Yeah. So diethyl malonate. So this is the ester of malonic acid. So I am writing CH3 CH2 CH3 CH2. Oh, that should be some O. C double bond O C H H. There is C double bond O CH2 CH. So this is diethyl malonate. Okay, in chemistry language, this is also known as like this DEM. Now you just undergoing ethyl. You are adding ethyl bromide. You just undergoing ethylation. Okay. So what will happen? These hydrogens will be replaced. Whenever you are using this diethyl malonate kind of thing, and you are just alkylating it in using this alkyl bromide or alkyl halide, what will happen? That it will just replace these hydrogens. Okay. So two kind of product I write just it at HCC CH2 O C double bond O C. I'm writing it CSC because one thing could be that it is replaced by only one ethyl group is enters here. This is possible. Another possibility is that both the hydrogens are replaced by ethyl. Okay. So this is the monoalkylated product, and this is the dialkylated product. Okay. So the question there is mentioned that alkylation of diethyl malonate with ethyl bromide gives two product, monoalkylated and dialkylated. You have to assign appropriate structure for each of the following compound. Okay. So you have to apply your logic to get to tell that which one is monoalkylated and which one is dialkylated. So first looking at the spectra, can you tell which one is what? Yeah, it is written already, but
The first compound A is dialkylated.
yeah. How can you know?
Based on the proton signals.
Number of signals, right?
Yeah.
So you see, going to the next here. Okay, for this one, okay, suppose, okay, it's already named as A and B. This is A and this is B. So in B, how much signals do you expect? For here, 1, this is and this is equivalent. Here 1, 2, 3, 4, 5. So 5 signals. How many signals you expect here? Here you see 1, 2, 3, 4. Because these groups are equivalent like this. Okay, so you expect 4 signals here. So just looking at this NMR's data you have given, you just clearly count how many different hydrogens are there. You see, in compound A, there is 4 different hydrogens, but in compound B, there is 5 different hydrogens, which indicates that A is the disubstituted one and B is the monosubstituted one. Now you have to assign which actually represent what. Okay. So now going one by one, for A, the delta at 4.2 quartet 4 hydrogen, which will be the quartet 4 hydrogen? If I name it, okay, I'm going one by one. So for A, suppose I am naming it HA. Here I am naming B. Here I am naming C. Here D. It is also A because equivalent there. B. Here C. Here D. Now you tell me that this 4.2 will be due to which proton?
B.
B. Because why not this one?
Adjacent is electronegative oxygen.
Yes, that will be very much descended. So it will be HB. Okay, this HB will be 4.2 quartet. How why it is quartet? Because there is 3 equivalent hydrogen. So 3 plus 1, 4. This will be quartet. Now to go to 1.9 quartet 4 hydrogen. Which will be this one?
C.
C. Yeah. Because there is another 3 hydrogen. So this is quartet. So this is why 4 hydrogen? Because here is 2. Here is 2. So 4 hydrogen quartet. And since this is not attached directly to an electronegative oxygen, so it will have lower delta value, 1.9. Now 1.25, 6 hydrogen triplet. Which one will be? A or D? A or D left. Which one it will
A.
be? A, right. So this will be H, C, this will be HA, and 0.8, it is only left one thing, this should be HD. Okay, so you have assigned all the protons in this compound A. Now coming to compound B, someone want to say something?
Sir, HD 6. Okay, sir. Triplet. Okay, sir. Okay.
Yeah, triplet.
Okay,
Because
sir.
2 hydrogens are there, no?
Yes, sir. Yes, sir. Okay. Sir, a triplet means that CH is having 2 plus 1, and N plus 1 is 3. That's why triplet, sir.
Exactly. Yes.
Okay.
Now compound B, you see again 4.2 quartet. Don't know which is this one. Okay, I'm last naming it. This is HA. This is HB. Similarly, this is HA, HB. This is, suppose I am naming it HC. Okay, new name is different. So this is C, this is B, and this is E. This hydrogen is E. Now 4.2 you have mentioned that it will be HB. What will be this? 3.2 triplet 1 hydrogen.
E.
Because this is not mentioned in the last spectrum data, and also why it will be 1 hydrogen triplet, because 1 hydrogen you can see, and there is nearby H2 group, so this will be 2 plus 1 3 triplet 1 hydrogen. Now this 1.9 quintet, two hydrogen quintet. Which will be
C.
this one?
C.
Why it will be quintet?
Because neighboring CH3 and other side it is CH. So 4 plus 1.
So why it is not doublet of the quartet? This is a quartet, right? CH3. This C, if coupled with CH3, this will be quartet. And if this coupled with this one, so this will be doublet of the quartet, right? So why it will be quintet, not doublet of the quartet?
I think it is not diastereotopic.
Yeah, but looking at the values, you can tell me J values.
It resembles a vicinal coupling of sp3 carbon.
Also, it is equal J value, that is mere magnetical equivalent. So this hydrogen and this hydrogen, you see all J values are equal, 8 hertz. So this hydrogen and this CH is their magnetical equivalent. So you will see that all these 3 and 1, this will be 4, and 4 plus 1 will give you 5. Okay, if they are different, then you will get doublet of the quartet. Okay. Now this 1.3 triplet 6 hydrogen, which one will be? 6 hydrogen triplet.
HA.
HA. And which one will be 3 hydrogen triplet? 19. This is only one thing left. H. So this is assigned. This way I have assigned all the protons in the compound, which will give you this kind of structure. Okay. Now, moving to the next question. The proton attached to carbon 1 of cis and trans isomer of 4-tert-butyl 1-bromocyclohexane appears at 4.6333 and 3.63 respectively. We have to explain the difference in the chemical state values of the C1 proton. And also, there is a follow-up question that would you expect to see such difference in cyclohexyl bromide? So let me first draw the structure of this 4-tertiary butyl cyclohexane. So this is one conformation, okay? C1, this means this one, and we are talking about this proton. Another conformation will be so which one is cis, which one is trans? Which one is cis, which one is trans?
First one is trans and second one is cis.
This is trans and this is cis. Because here you see both tertiary butyl and the bromine will be in the same direction. It is cis, and if it is opposite direction, this is trans. Okay. Now the question is, you see here hydrogen is axial hydrogen, and here hydrogen is equatorial hydrogen. This is a very fairly simple. So which actually corresponds to 4.33 and which corresponds to 3.63 ppm chemical state. HA will correspond to which one?
Sir, 3.6 for axial hydrogen, sir. Trans
3.6
for trans axial hydrogen, sir.
axial hydrogen.
Yes, sir.
And higher one will be
4.6.
equatorial.
Yes, sir. Higher for equatorial, sir.
Why?
Sir, in the SARS previous slides, I am observed when the hydrogen is in axillary position, that almost shift values are in lower size. Based on observation, I told.
Yes, yes. Anywhere you in any kind of cyclohexane or air kind of system, you will see that your equatorial one will be most distributed compared to the axial one. Why that happens? One reason, just one thing. This is the sigma bond anisotropy. I have explained the same question in the previous week assignment also. The sigma bond anisotropy will give you this HA and HE that will be different here. Okay, the HE that will be more distilled because it is parallel to this sigma bond, and hence this will be more distilled. So this will become at higher delta value. But so if you have explained that what kind of observation you will see when you have 4 tertiary butyl 1 bromocyclohexane in cis and trans form. Now the follow-up question is, would you expect to see such difference in cyclohexyl bromide? What is cyclohexyl bromide? Cyclohexyl bromide is the same thing but without a tertiary butyl group. So here this is another one conformation. This is another conformation. So suppose here is HA. HE. So in this case is done. You have correctly explained what will happen in this case. Now coming to the right side, where there is cyclohexyl bromide, what you will expect? There will be 2 different protons. What do you expect?
No, sir, there will be one type of proton.
Why?
Sir, the second one is more stable and the first one is less stable because 1,3-diaxial repulsion.
You are correct. Here 1,3-diaxial repulsion is there. Here you are talking, right? This one, huh?
Yes, sir.
Yes, but yes, you are correct. This one is less stable. This one is highly stable. So you will see the ratio. Suppose you will see the ratio of 80:20. Maybe you are 90:10, right? Less stable doesn't mean that it doesn't form, but the ratio is very less. So you will see some difference for these 2 hydrogens.
There should be some difference if the ratio is 80:20.
Okay. Anybody else? Anybody else?
Sir, is there will be conformational interchange? Axial to equatorial position?
Yes, that will be there. What's your name?
Sir, Prakash Mandal.
Oh, again Prakash, okay. So there is a conformational change as Prakash mentioned, but here is also there is a chance of this conformational change. But why there is no conformational change happening here?
Sir, due to tertiary butyl group, this is a big group.
Exactly. This tertiary butyl group actually locking your one conformation. Okay. So this tertiary butyl, in presence of this tertiary butyl group, it cannot put it in the axial position because there will be severe 1,3-diaxial interaction. So you need to put it in the equatorial position, and putting it in the equatorial position, then you can adjust what will be a position of the other atoms. But when there is no tertiary butyl group, a fast exchange between these 2 will happen. So what we will see, you cannot differentiate that during flip, this will happen so fast, you cannot differentiate it. You will only end up with one peak, which is the average Raoult peak of these 2. Okay, this will come like at 4 or 4.1 kind of thing. Okay, so for 4-tertiary-butyl 1-bromocyclohexane, the difference in the chemical shape for axial equatorial proton appears due to the sigma bond anisotropy, what I have said to you. but equatorial hydrogen comes at 4.33, axial hydrogen comes at 3.663. However, for cyclohexyl bromide, due to fast flipping of the cyclohexane, both this axial and equatorial are becomes indistinguishable. We will see only one peak. Okay. Does anybody have any question?
In the second picture, at low temperature, there may be two different peaks.
Sorry, I cannot get your question.
This conformational changes at high temperature. But what happens when the temperature is low? There may be the
You
chance
are
of
asking about low temperature?
yes.
Yes. In the low temperature, you will be able to distinguish between these two. Okay, just like in any kind of cyclohexane, you can be able to differentiate between these two structures. Okay, below this coalescence temperature, you will be able to differentiate between this one and this one. But at room temperature, what will happen that this structural transformation is so quick that you cannot differentiate between these two. So only one peak you will get. Okay. Okay. Next question is this one. When aniline is chlorinated, a product with the formula C5H5NCl2 is obtained. The spectrum of this compound is shown below. This spectrum is your eye is not capable of resolving this. So I have written the values. Delta is 4.1, 2 hydrogen broad signal, 6.65 doublet, 1 hydrogen, J equals to 8.6, 7.02 doublet of doublet, 1 hydrogen, J equal to 8.6 and 2.3, and 7.23 doublet, 1 hydrogen, J equals to 2.3. You have to determine the structure and also explain what the property, the compound, and assign each state of these peaks. Show what kind of compound it could be. I just give you some hint, then you think and you will answer me. So your question is, you have aniline. Okay. You are just chlorinating it. So you will end up with something. I'm not writing what is this. I'm just writing the formula. Okay. And also the this compound, this NMR spectrum is given. Now you have to find out what kind of compound is this and what will be the pattern.
Is it 2,4-dichloroaniline?
How do you know?
Amino is orthopara director.
Yes. Correct. Sorry. Okay. So yes, is it correct? The structure will be like this. 2,4-dichloroaniline. Because it's correct. This is NH2 group is the orthopara orienting group. Now, from this NMR spectra, if you don't know, how can you get this? First, see, brought 2 hydrogen 4.1 spectrum, brought 2 hydrogen spectrum. This is actually, broad spectrum actually comes from these exchangeable hydrogens that I have mentioned in the previous assignment also. These exchangeable hydrogens actually give you this broad signal. So in your product, since you are getting 2 hydrogen broad signal, it is coming due to your NH2 group. Okay. This is first thing is confirmed. NH2 is already there. Now the second thing, you see a doublet at 6.65. Okay. 1 hydrogen doublet and J is equals to 8.6. And here you see a doublet of doublet of 7.2. So which is the actually the what do you say, the aromatic region where you will see this double of doublet. But here you see 2 coupling constant. So what is the two coupling constants. If I write in this structure what I have given here, suppose I am writing it HA. This is HP, HC, HT. Okay. So if I have some knowledge, I can tell that the J value of 8.6, nearly 9 or 10, it corresponds to orthocoupling. Corresponds to orthocoupling. J equals to 2 to 3. This actually corresponds to metacoupling. Sorry, not paracoupling. Very poor. Metacoupling. So you see for this 7.02 peak, you see two types of coupling. So this is a very high chance that this proton is involved in a orthocoupling, as well as in a metacoupling. So which among B, C, and D is involved in meta as well as orthocoupling? Which one?
HC.
C.
HC, exactly. So this is the HC. This is orthocoupling with this one. This coupling constant is how much? 8.6, yeah. And this one actually gives 2.3. Okay. Now you see there is one here, so this will be doublet, and since it is metacoupling with this, so this will be doublet of doublet. Now you have explained that HC it will be doublet of doublet, and this will be 7.02, right? 7.02, right? Now you have identified this one. This will be how much? This will be 4.1. Now you have two signals left, 6.65 doublet and 7.23 doublet. You can easily tell which one is HB and which one is HD. So 6.651, which is this one, HB or HD?
HD.
HD, yeah, this one. Why this one?
Same J value, sir.
Same thing, yes. This is the value of this orthocoupling. So it is coupling with this one. So this must be this one. So it will show how much pattern this is doublet. And here you see there is the meta position is blocked. So it will see only doublet. You will see that 6.65 there is a doublet only. So this will be doublet of doublet. Sorry, this will be doublet only. Now this B, this one is only the thing left, that is 7.23. So one hydrogen is there, but why it should show doublet? Because there is no hydrogen in nearby, so it will should show singlet. But due to this metacoupling with this CHC, which is a value of 2.3 Hz, it will show a doublet kind of structure. So this is the compound 2,4-dichloroaniline. Is it clear?
Here, sir, here the main point is the chemical shift value comparison. HB has greater chemical shift value than HC than HD. Due to,
Yes.
sir, in minus I effect of chlorine maybe?
Yes. Gishilding John, yes, you are correct.
Thank you, sir.
But also from you can easily assign it using this coupling constant. Coupling constant actually gives you a very lot of information. Okay, whether this is ortho-oriented or para-oriented or meta-oriented, you can easily get it from this coupling constant. Okay.
Yes, sir. All this confirms this.
Okay.
Can I have a question, sir?
Yeah, sure.
In case if you take this particular 2,4-dichloroaniline,
So 4
And if-
dichloroaniline, yes.
yeah, and if it has been taken the spectrum at a lower temperature,
We want to low temperature. Yeah.
what will happen to the coupling of HD and amino group? Will be having any coupling or not?
Coupling between HD and amino group.
Yes,
In principle, you expect there's coupling.
because
There
that's
will be
not
four
a
bond
total
coupling,
picture.
but it will be very weak coupling.
Yeah, generally we have seen that in the lecture that the protons attached to any of these heteroatoms
Mhm.
being very faster at a room temperature, we are not able to get a coupling. That's why we get a broad singlet.
Yes, because this actually exchanges with the solvent.
Now, at the same spectrum, if you take it at low temperature, will you have this kind of coupling interaction between this amino group and this HT?
Yes, in principle, you will see that. Okay, but the coupling strength will be very low. This will be because 4 bond coupling. See here. Okay.
Yeah, means it will be difficult to.
What I am saying,
Yeah.
that if hydrogen is attached to hydrogen, if suppose there is some hydrogen here, then you will see a much strong coupling. But since they is far away, the coupling strength will be very low. But in principle, you go to low temperature, and if you are dissolve it in a solvent that can exchange proton with this one, then you expect to see some coupling. Yes.
If the same thing has been taken in NOE,
NOE.
nuclear overas reference.
Yeah, for then you need to just apply this any kind of proton frequency or stop that. If you go to just at a low temperature, you just put here this one, this HD, you just put frequency here, NOE here. So you see that if this is changing, then you will understand that if there is coupling happening or not. But since it is through space, so the coupling also will be very weak. If it is there, then coupling will be very much strong. Yes.
Yeah. Thank you. Thank you.
Coming to the last question for today, there is 6 isomer possible for bromostyrene. You have to identify the isomer to which the following one HNMR spectrum belongs. So you have to assign this A to E for the various protons in the structure. So styrene is actually looks like, what is the structure of styrene? What is the styrene kind of structure? Forget about bromo. What is styrene?
C6H5CH double bond CH2.
This one?
C6H5CH double bond CH2.
This one, huh?
Yes, sir. Yes.
Yes. Okay. So this is a styrene. Okay. Now, if you go with bromostyrene, so why we will have 6 isomer? You can see from the structure of this styrene. Okay. You see there are 6 different protons that you can replace with bromine, right? If I'm not wrong, you can see there are 6 different protons which you can replace with bromine. This one I can replace with bromine. Okay. This one I can replace it with bromine. This one I can replace. These two are equivalent. This one and this one is equivalent. I can replace them. This one and this one is equivalent. I can also replace them. And this is an different. Okay. So 1, this 2, 3, 4, 5, 6. So 6 isomers corresponding to 6 position of bromine is possible for bromostyrene. Now you are given some NMR data from which you need to know which kind of which isomer is here. Okay. So in a clear case, I'm just writing. Drawing a 6 isomer is very difficult here. So I'm just writing in a simpler way so that you will be able to understand. So here, what is happening? Okay, so first isomer HA is replaced by bromine. You see here, right? HA is replaced by bromine. Second isomer HB is replaced by bromine. Third isomer HC will be replaced by bromine. Fourth HD will be replaced by bromine. Fifth one HE replaced by bromine. And sixth one will be HF will be replaced by bromine. Okay. These six are the possible isomers of bromostyrene. Now you have to find which one corresponds to this NMR. Okay, since you have a lot in your set, you have a lot of data, so you need to subtract some of them and make your life much more easier. So what will happen? What we will do? Sorry, you take NMR. You take the count of how many different protons are here. You see A, B, C, D, E. 5 different protons. You see 5 different protons, right? Now, okay, you need to go to okay, I'm drawing all the structures, then it will be helpful for you. So structure 1 will be bromine here, hydrogen, hydrogen, this is one. Next structure, this is structure 2. Structure 3. Oh, sorry. So one by one, I am replacing the hydrogen with bromine. Okay. Now this is structure 4. Either side, okay. You can put it here also. Four. This is 5 and oh, finally. Yeah, I have drawn all the 6 possible isomers from which you will just need to match it with your NMR data. So now I am just need to count how many different protons are there. Okay. So in the NMR, I have seen only 5 different protons. Now you need to count how many different protons are here. First here 1, 2, these 2 are equivalent, 3, these 2 are equivalent, 4, 5. Here is 5. Here 1, 2, 1, 2, this 2 equivalent 3, this 2 equivalent 4, this is 5. Again 5. Here 1, 2, these two are different. Okay, 3, 4, 5. That is also 5. Okay. Here 1, 2, 3. Is this two? These two are equivalent then? No. This and these are different. This is ortho to bromine and this is para to bromine. So these are different. So 1, 2, 3. This is 1, 4, 5, 6, 7. Now 1, 2, 3. Here the same thing. 4, 5, 6, 7. Here 1, 2, 3, 4, 5. These are equivalent because here is bromine, this is ortho to bromine, this is ortho to bromine. Okay, so 5 here. So now you see 5 different protons are present in the molecule. So these two actually you can neglect because there are 7 different protons. Now these 3 among these 3 structures, just go. Now you see in the aromatic region, what is the aromatic region? Above 7, right? Above this 7, this aromatic region, what you can see just a doublet and 2 doublets, which is known also, you can say AB quartet kind of thing. You can see here AB quartet kind of here, this region, you can see AB quartet kind of structure, and these values are 7.2 and 7.7. 7.3 and 7.2 like that. Okay. So in the aromatic region, you are only seeing AB quartet kind of thing, and also you are seeing 2 signals only. Okay. Suppose if this is your structure, you expect to 3, 1, 2, 3. Okay. This 3. If this will be structure 1, 2, 3. If this will be a structure 1, 2, 3, that means in aromatic region you are expected to see signals. Okay, above 7. Fine. So since you are not getting that, you are just neglecting this one. But also you need to verify that whatever is remaining is that matches with the given in our data. And also, since you are getting AB quartet kind of structure, which actually gives you information that there is a para disubstituted compound, right? Whatever I have told you in the first assignment, this is a para disubstituted compound. So most probably this is the structure, and here this corresponds to this near level to bromine. So this will be 7.3. One is there and 7.2 is this should be one. Now these 3 you can easily distinguish them. Which one is which one? You see, this is a nothing but a doublet of doublet. Okay, it is looking like this. So here you see, if in this case, now if this is the structure, so this HC, what will happen with HC? It will find no proton here, so it will couple with this, it will couple with this. So you expect that this is 2 hydrogen triplet, so this will be 1 hydrogen triplet, but not, this will not happen because these 2 hydrogens are different. These are diastereotopic hydrogens. So you know this diastereotopic hydrogen, so this coupling strength will be different, so it will give you doublet of doublet. And also this doublet, since it is very closer to this aromatic ring, so it will be very much distillate. So whatever you are seeing at 6.7 kind of thing or 6.8 is multiplied, whatever you are seeing here 6.6, 6.7, this multiplied, this is actually coming, this is nothing but a doublet of doublet, and you will see that this is coming due to this HC. Okay. Now, what about two remaining? This D and E, you just see between these two protons. Okay, this is one H. Suppose I am naming it HD, and suppose I am naming it HE. Okay, so which one is D and which one is E? So if I give you the value, one is at 5.8 or 5.9, 5.8, and another is at 5.1, 5.2. So which is HD and which is HE?
HE is 5.8 due to transcoupling.
Due to transcoupling, this delta will be high. H, which
Yes,
one?
sir.
Which one you are telling? HD.
HE
H is 5.
which is trans to C.
Mhm.
5.8. Yes, sir.
Yes. Also, you can confirm it from this data that you see the coupling constant here and the coupling constant here. This is a very high coupling constant. This actually denotes that your whatever you are seeing, this HD D1 is the trans one. Okay. So your trans one will be very much decelerate. So your TC will be whatever D or E, they are nomenclature. So according to their nomenclature, this D and this. Okay. So whatever you get, this is the structure. I'll just rub it off. This is the isomer, what I was talking about, of bromostyrene, which will give you peaks like this. Okay. So any question after this? Okay. So if there is no question, then yeah.
So I just want to have a clarification.
Yes.
The assignment what is been given to all of us, particularly number 3.
Yes.
Please check with others also. We got only 4 questions, each of 5 marks, but the total marks is 25.
But number distribution is what you are telling about this number distribution, right?
Assignment number 3.
You are telling about this number distribution in the question, right?
No, we have got the assignment number 3 and we got only 4 questions. Each question it was given as 5 marks each, and I don't know whether one question is missed out or we have to distribute.
The number given is wrong, but 4 questions are there. Yeah.
Okay.
I can clarify, sir.
Yeah.
The fourth question has 2 parts, and each part contains 5 marks. So 4 question is of 10 marks.
So that is given wrong at 5 marks.
Okay. Got it.
Okay. So,
sir, I have a doubt.
Yeah, sure.
The molecule bromostyrene, which we found out, sir, there is no plane of symmetry. That is, these are para substituted, but different groups. The lower group is bromine, and the upper group is the olefinic part. So there is no plane of symmetry. Then how can we say that there are 2 types of protons?
Yes, there is plane of symmetry. If it passes to this one, if you suppose, like if you okay, like this, okay, if you see your benzene ring, you can see my pen.
Yes, sir. Yes, sir.
Yeah. So here you see my finger. This is your, suppose here double bond, and this is your bromine. Okay. Here is
Yes,
another
sir.
hydrogen, and another hydrogen. So if there is some plane passing like this, cutting the bromine half. Okay. If suppose you this bromine is here like a ball, and if is cutting it half, and it is also cutting the double bond is half, you will see there is a symmetry. It is passing through this allylic double bond and also bromine. Okay. Just like you suppose if you have instead of this double bond, if you have suppose methyl group, okay, one is methyl, another is bromine. So you will have a symmetry. This symmetry the plane will pass through this methyl and bromine, okay, and this will cut this methyl and bromine into two halves.
Okay, sir. Got it, sir.
Got it?
Thank you.
Yeah.
Yes, sir.
It is passing through that. Yes.
So will you solve a problem for carbon 13 NMR in the next assignment, sir?
Yeah, I need to check what is given in the next assignment, and then I will solve. I think there is problems regarding carbon 13. I'll solve in the next assignment.
Okay, and also you'll be explaining about the spectral pattern of compounds at two different temperature based on dynamic process.
Which one?
No, the spectral pattern of the NMR at two different temperature based on the dynamic process.
That I have explained, right?
Yeah, okay.
Okay, so I for the recording part.